Okay, hello everyone. My name is Dr. Randy Davila, and I will be your instructor for Math 2409, Introduction to Proofs. So this course is designed for math majors and is the beginning of what I would call like real mathematics. Proof and argumentation, that's really what a mathematician does. And as math majors, all of you need to understand how these things work. So I'm going to go ahead and share my screen with you right now. Okay. All right. And we'll go to the Blackboard page. So if I go to my syllabus here, okay, so let's make this a little bit bigger. Okay, so this textbook here, I have yet to get from the company, but I will get that information for you to purchase this book. So just check Blackboard and you'll see the purchase information then. I think it's $58. It's all online.
That is my counter argument. Which is really just me apologizing for being a jerk. And talking about how much your friendship means.
Got it.
And how much I missed you. And how co-parenting has to be our top priority.
That's the thing, Mateo.
And that's in section 2. A list about how it would ultimately benefit him.
Whose type is up?
Just continue reading.
All right. Okay, so we're good. This textbook information will be provided by the end of the day after the company gets back to me. And then this other textbook here, this one is an expensive textbook. So I wouldn't, like, you can buy it if you want, and you probably do want to own it. But if you don't, you can find a PDF of this 6th edition of this book online. If you just search around, I'm sure there's a PDF somewhere. I know that I found one before. And I'll be using this as a supplemental book in my lectures when I record these lectures. My phone number here, you can just ignore that because I won't be in my office at all this semester. I don't think anyone's going to be at their office. So what I would like would be if someone would make a GroupMe account for all the students in the class, and then just send me the GroupMe link, and I'll be a part of that. That way, if there's an emergency that happens during like a weekend and you're taking a take-home exam and you don't understand something, you can just send me a text via the GroupMe message board, and I'll be able to answer it, provided it's not like 11 o'clock at night or something like that. Okay, so what are we going to cover? So the beginning of the class, we're going to cover logic. We're going to spend about 3 weeks on just logic and combining that with proof techniques. And then we're going to go into a little bit of set theory. So we're going to look at proofs in set theory, proofs in number theory after that. And then the main goal of this course, really for me, when I teach this course, is right here. Proofs in abstract algebra and proofs from real analysis. So those 2 courses are required for all math majors, and they're kind of like the pinnacle of an undergraduate degree in mathematics. So taking abstract algebra 1 and 2, or taking real analysis 1 and 2, those are going to be your most difficult proof-related courses. So it's my goal that by the end of this semester, all of you have been exposed to proof techniques in both of those courses. Okay, because those are the courses that students will struggle in the most. And we're going to do some pretty difficult ones. I'm not going to ask you to prove anything on your own, but I am going to ask you at the end of the semester to memorize some rather intricate proofs. Okay, so that's the goal. And if we have time, I'd like to give proofs in graph theory, just because my PhD is in graph theory. And on that note, I almost forgot, not being in person is throwing me off a little bit. I have a PhD in mathematics, but I started as a high school dropout. I dropped out of school on my 17th birthday because I was so far behind in my mathematics courses. I ended up getting my GED. Someone's mic is on again. I ended up getting my GED, and I worked as a truck driver. But then, after a while, I decided I wanted to go to school, and I was always really bad at mathematics, so I thought I wanted to be like smart, right? And I thought smart people did math, so I decided I was going to try to major in mathematics. So I got my GED and started at community college at like the lowest level math course they had. It was pretty low, math of 308, I think. Wasn't even a college level course. And I worked my way up, and eventually I made my way to U of H downtown. And I ended up earning a bachelor's degree in applied math from U of H downtown in 2012. And because of the close contact that you can have with the professors at U of H downtown, I was able to actually get a mathematical publication with one of my professors as a senior. So after graduating, because I did well in my later courses and I had this publication, I was accepted to Rice, where I received a master's degree in computational and applied mathematics. From there, I went to be a lecturer at Texas State University for 3 years, while also working on my PhD, and then came back to U of H downtown as a lecturer. I finished my PhD in 2019, and in the fall of 2019, I started as an assistant professor of data science. That's my official title. So I came from UHD. I love it, and I have a particular interest in helping students succeed at UHD. Because a lot of students at UHD are non-traditional. I was non-traditional, and because of the professors at our university, I was able to do things I never thought I could do. So I have a real fondness for our students. So please, throughout the semester, if you're ever struggling, if anything happens, especially like during times of coronavirus, like if someone in your family gets sick, or just if anything happens throughout the semester, just please don't hesitate to contact me, and we can figure it out. I don't want anyone dropping the course and giving up. It can be difficult at times, but please reach out to me if you can. Okay, so back to the grading policy now. So there's going to be quite a bit of homework that I'm going to assign through the Zybook. So this is all online, it's interactive, but I think that just going through the homeworks, that's going to help a lot. There'll be 2 take-home exams. And then I mentioned a final project here. This might just be a final exam, or it might be putting together a little portfolio of proofs that you can scan into a single PDF like you write, and then send that to me. So it's either going to be an exam, or it's just going to be a collection of proofs that you put together, and maybe like a writing assignment that you'll have with that. I haven't yet decided. Again, this is new to all of us, working remotely like this. So this is going to be very flexible. Things are going to change. But just know that because of this, I'm going to be I'll be particularly lenient on the grading and stuff. because we're going to have to work together on this, right? All right, so, okay, now as far as using Blackboard, so there's going to be course content here. Actually, let me make a folder real fast. So I'm recording this this lecture right now, or this video. I'm going to put it in this folder after we end. Now, here in this YouTube videos link, I'm a big fan of YouTube. It's one of the best ways to supplement your lectures. In fact, like up until like your junior year, you can probably teach yourself everything you ever wanted on your own just by using YouTube. It's not until your senior level classes where it becomes a little bit more niche and you won't be able to find help. But for example, here, if you click on this logic videos link, so this is a series of videos that I found. They're going to mirror what we're going to do in lecture. So videos 1, 2, 3, 4, and then 7, 8, 9, all the way down to 21. That's basically the first 2 weeks of our course. Right, so the only videos in this series that you wouldn't really want to look at are videos 5 and 6. Those are the only two that really won't match up with what we're doing. So I highly encourage you to watch these videos. And pretty much anything that I post in the YouTube videos folder, you're going to want to watch. As math majors, you're going to want to watch. Some of them might not necessarily be directly applicable to this course, but they will be to your major. And they will help you understand better what it means to be a math major and what it means to do mathematics. So like this is a video that all of you should watch today. It's nothing that you would take notes on, but it kind of gives you like an overview of the field of mathematics that I think you might like. Okay. And then again here, I'm going to put all of my lecture videos here. Okay, so I suppose we should get started with actual lecture. So let me okay. So this would be I'll call this section 1. So section 1. Logic. So in order to write mathematical proofs, we need to build up a foundation in logic first, and then formal logic, and in particular, propositional logic. So there's going to be a lot of definitions. I'm just warning you ahead of time. There's going to be a lot of definitions. So the first definition is that of a proposition. So a proposition is a declarative statement that is either true or false. So I'm going to denote true with a capital T and false with a capital F. Okay, so this is the definition of a proposition. Okay, now, so an example would be So UHD is a public university. And so this is a declarative statement. It declares something, and it is either true or false. In this case, it happens to be true, right? Now, when dealing with propositions, we're going to treat them in the abstract often, and we're going to denote them with lowercase letters. So I'm going to write a little p here. So P, and this is like a logical equal sign. We'll get to what that means later. But P is this proposition. UHT is a public university. Okay, so the next definition is the negation of a proposition. So the negation of a proposition P, so lowercase p is some proposition. The negation of a proposition P is the proposition it is not the case that P. So it is not the case that P. So this is the negation. Now, there's a notation to this. So if P is the proposition that we're negating, this is written like this. And this reads not P. Okay? So that's the proposition P, this is not P. All right, so if this here is our P, UHD is a public university, the negation of that, it is not the case that UHD is a public university. Okay? So notice now, so P is true in this case. UHD is a public university. It's a true proposition. Notice that the negation of it, it is not the case that UHD is a public university. That is false. Okay? So this leads me to our first truth table. Okay, so P and not P. So if P is true, then the negation of P, not P, must be false. If P is false, the negation of P must be true. Okay? So this right here, this is called the truth table. And it's just a table that expresses the relation between a proposition and some operation on that proposition. Okay? All right. So it's a fairly simple concept, and the textbook that I'll have ordered for you will go into like examples of propositions and what's not a proposition. But just think of it a declarative statement that's either true or false. Okay. So now that we have this notion of propositions, we can now define operators on these propositions. Okay, so I'm going to do that now. Okay, so I'm going to do this rather in a concise manner because I have such a small whiteboard. So let me write down a big truth table, and then I'll explain the operators after I write down the truth table. So P is some proposition, and Q is some other proposition. Okay? So P could be true, and Q could be true, right? P could be true, Q could be false. P could be false, Q could be true. And then finally, they could both be false. Okay, so given two propositions, these are all the possible combinations of truth values that these propositions can have. Okay? So now I'm going to define some operators. Okay. So let me fill these in, and then I'll tell you what they are. Okay, so these symbols here are just operators between those two propositions. And you're familiar with these things. Like think about the operators on numbers, right? You have the addition operator, you have subtraction, multiplication, division. These are operators on numbers. Well, we can define operators on propositions. So here, right here, this is the disjunction. So disjunction. Right there. And this reads P or Q. P or Q. P or Q. And this operator is true whenever at least one of P or Q is true. So look here. So read left to right. So here's P, here's Q. So if they're both true, it's true. True or false is true because at least one is true. False or true is true because at least one is true. False or false is false because at least one of them has to be true for this disjunction operator, the or operator, to be true. Okay. Here we have the conjunction. And this reads P and Q. Okay, so P and Q is true only when they're both true. Okay, so we look at the truth values for P and Q here. So true and true is true because they're both true. True and false is false because one of them is false. False and true is false. False and false is false. Okay, so that's the conjunction. Okay, so here we have the conditional. And this reads, if P, then Q. So if P, then Q. Another way of saying it is P implies Q. That's another way of saying that. And I'll use both interchangeably. Okay. So this is going to be really important for us because most mathematical statements that we're going to prove are of this form. If something, then something. For example, if x is even, then x squared is even. We're going to be proving things like that. So this is really important, and we're going to spend a lot of time focusing on this operator. So this operator is only false when, oh, I almost forgot. Here, P is called the hypothesis. Okay. So P is the first proposition is the hypothesis, and the last one here, that's the conclusion. Okay. So if then, so if hypothesis, then conclusion. Okay. So the conditional is only false when the hypothesis is true and the conclusion is false. So if we look at this row here, if true, then false, we see a false right there. So that's the only case where it's defined to be false. All other cases, it's true. In particular, and always remember this, if you have a false hypothesis, you always have a true statement in the conditional. Okay? And then true implies true is true. The only one that's false is when the hypothesis is true and the conclusion is false. Okay? And finally, we have the biconditional. And this reads P if and only if Q. Okay. Now, because we're going to encounter this one a lot as well, and it's kind of a lot to write if and only if over and over, I'm going to adopt the common notation, if you will. So if I write IFF, that's an abbreviation for if and only if. So please remember that because I'm going to use it throughout the semester. Okay. Now, the biconditional statement is true only when they both share the same truth value. So notice here, true if and only if true, true. True if and only if false, false. False if and only if true, false. False if and only if false, true. So if they have the same truth value, then the biconditional is going to evaluate it true. Okay? Okay, 1 second. Actually, before I move on, I need to talk a little bit more about if P then Q. So, okay, so if P and Q, so this is the conditional statement. So, so if this is your original conditional statement, this is a very special version of it. This is called the contrapositive. And so contrapositive, I guess, of if P then Q. So remember this symbol from before? This is the negation, right? So the negation of the conclusion implies the negation of the hypothesis. That's the contrapositive of if P then Q. So this is really special because let's just make a truth table so I can describe this. Okay, so we have true, 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 false, false, true, false, false. Okay. So again, these are all the possible combinations of truth values for the propositions. Again, remember propositions are either true or false. So the conditional, if P then Q, right? Remember what I said, this is only false when the hypothesis is true and the conclusion is false. So true implies true, true, true implies false, false, false implies true, true, and then false implies false, true. Okay? Now, take a moment and see if you can fill in the values here without me doing it. See if you can fill in those values. So what would go there, what would go there, what would go there, what would go there? Okay, so let's look at this first entry right here. So not Q implies not P. So look over to Q. So the negation of that right there would be a false, right? So not Q is false, implies not P is false. So it'd be false implies false, which is true. Right? I guess it might be easier, instead of filling in this right here, I don't want to rush things too much. We can just go ahead and make a not P and not Q column, and then a not Q implies not P column. That way it'll be easier to see, I guess. So if P is true, then not P is false. Let's see a false there. If that's false, this is true. True. And then not Q, so it would be false. So then this would be true, false, and then true. Right? I'm just negating whatever I see there and just changing the true to false or false to true. All right, so now I can look at this. So not Q implies not P, so that implies that. True. That implies that. False, right? Because a true hypothesis implying a false conclusion, that's a false statement. And then false implies true, that's true. True implies true. True. Okay. So what I want to point out is,
I'm sorry. So do you read it like from Q to P, or are you reading it from like P to Q? Because I see like you're pointing out first the Q,
right.
the Q to the P.
I am.
Huh.
But here I'm starting with that, right? That's the, so that implies that. So
Okay.
That implies that implies that implies that.
Gotcha. Thank you.
Mm-hmm. So now I want you to notice now, look at all of those truth values. True, false, true, true, okay? And look at all of those. True, false, true, true. And again, we're reading from left to right. Like, these are combinations of true and false for P and Q. So with each of these combinations, we have an associated value for that operator. Again, for each of these combinations, we have an associated value for this, right? Notice that they're the same. Both these columns match up. Can you see that? True and true, false and false, true and true, true and true. Right?
So does that mean that the contrapositive of P and Q will always be the same as the conditional of
Exactly.
Q to P? I mean, of P to Q?
Exactly.
Okay.
So this is a really important thing. This is logical equivalence. I'm about to describe what that means in a second formally. But this is informally, with this truth table, they match up all the same. Right? Which means that they're always going to have the same truth values. No matter what combination of P and Q that you have, they're always going to have the same. So what this means is that later on in the semester, if we're trying to prove a statement if something then Q, that's the same thing as proving the contrapositive. And sometimes the contrapositive is going to be much easier to prove than the original statement. And we'll see examples of that later on. But first, I need to describe what that symbol means. This logical equivalence symbol means. Informally, it means that the two compound propositions match up in a truth table. That's the informal way. Okay, so more definitions. Okay, so a tautology is a proposition or compound proposition. So again, a compound proposition is just propositions that are linked up by these operators I've described. So a tautology is a proposition or compound proposition that is always true. Okay? So that is a tautology. A contradiction is a proposition that is always false. Okay? So that's a contradiction. Okay? And a contingency is a proposition that it depends. Okay? But that's a less used term. But again, contingency is one that is either true or false. It can be either one. Okay? So let's look at some examples. Okay, so I'll say A, the proposition, okay. Okay, so we have some options here. Which of these is a tautology? Something that's always true. So this or guy right here, right? The disjunction between propositions, that's true whenever what? At least one of the propositions is true, right? So true or Q, it doesn't matter the truth value of Q, does it? If Q is false, this would still be true. If Q is true, it would still be true. So no matter what you do with the truth value of Q, this is always going to be true. So this would be a tautology. Is there another one up there?
Would it be D?
Which one?
D.
So D, so we have false or Q, right?
Mm-hmm.
So if Q is true, you'd have false or true, which is true. But what if Q is false? If the truth value of Q happens to be false, what does this evaluate to?
That would be false.
Right? So that's not always true. What about this one? The conditional statement is only false when the hypothesis is true and the conclusion is false. So whenever you have a false hypothesis, you're always going to evaluate to true, no matter what. If Q is true, it would still be, this would evaluate to true. If Q is false, this would still evaluate to true. So these two right here are tautologies. Okay. Are there any contradictions up here? Any contradiction, something that's always false. What about A? If P was true, right, false and true, that would be a true statement, right? No, that would be a false statement. Because in order for the conjunction, the and, between two propositions to be true, what has to happen? They both have to be true. But here, this one's always false, so this is always going to be false. It's always going to evaluate to a false statement. So this right here, that's a contradiction. And because this, no matter what you plug in for P, the value, true or false, this is always going to be false. So that's a contradiction. Okay? And then here, this will be a contingency because the truth value of this compound proposition depends on the truth value of Q. If Q is true, this is true. If Q is false, this is false. So it's contingent on the truth value of Q. So that's again, a contingency. Okay. Okay, so now we can talk about logical equivalence. So, okay. The two propositions P and Q are logically equivalent that's written with that symbol I was using. Whenever P if and only if Q is a tautology. Okay? So, for example, so if P then Q is logically equivalent to not Q then P, or not P, because if P then Q, if and only if not Q implies not P. So you can treat these as like their own propositions, right? Because that is a tautology. And if you look in your notes, when I had the truth table involving that and that, right? These always had the same truth value for the given combination of P and Q, which means that the entire column, if you did a column for the if and only if between these two, would be all truths. Okay. So remember, the biconditional operator is true whenever they have the same truth value, right? So if you look to that table and you look at this column and that column, they always have the same truth value. So if you would have filled in another column with this biconditional, that entire column would have been all truths. It would be a tautology. It's always true. Okay. Okay. So let's look at another example just so we can like kind of really nail down what it means for this to be a tautology. Okay, so I have a claim. The negation of P or Q is logically equivalent to the negation of P and the negation of Q. So that's my claim. It's not focusing. There it goes. Okay. So we're going to prove this with a truth table. Okay. All right. So it's going to be kind of a big truth table. Okay. All right, so true, 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 false, false, true, false, false. Okay, and there's going to be one more column. Let's forgot. Okay. So let's go ahead and fill this in. So the or is true whenever at least one of the propositions is true. So true, 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 false. Okay. And then here we're just negating that. So the negation of each of these, so this negating that would be false, 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 true. Okay. Then here, this one we have to kind of think about. So not that and not that. So that would be false and false, which is false. So not that and not that. So false and true, still false. So not that and not that, again, so true and false, still false. And then finally, not that and not that, true. So true and true. Okay. Now, if we look over here to the biconditional is true whenever they have the same truth value. So we're looking at that if and only if this. So false if and only if false, good, that's going to be true. False if and only if false, true. False if and only if false, true. True if and only if true, true. That's like the finishing of the proof, the little box. But just notice here that that column is all truths. So the biconditional between these two things is always true, which means it's a tautology, which means that we can justify writing that simple. Okay? Okay. So, oh, this actually has a name. So there's two parts of this actually. Thanks for that. These are called De Morgan's laws. So, De Morgan's laws. So the negation of the or becomes the negation of the disjunction becomes the conjunction of the negations. The negation of the conjunction becomes the disjunction of the negations. So those are called De Morgan's laws. So I encourage you to verify this one right there on your own. We did that one. It's not that hard to do that one. Okay. Okay, so I think that will be it for today. I need to get your textbook information for you. That way you can start reading through the textbook and doing the homework problems. So real quick though, let me just search for something. Oh, and obviously start watching those YouTube videos. No, it's not going to do. There's one somewhere. I don't know where it's at. I'm looking for it. Yeah, found it. So if you want to read along with the notes that I'm kind of basing all of this off of, from the 7th edition book, I would say sections 1.1, 1.3, 1.4. Well, we didn't get to 1.4 today, but we did 1.1 and 1.3. That's what we began talking about today. So if you want, I would find this book online and go ahead and read 1.1 and 1.3. Okay. And I don't know if I'm allowed to post these links on Blackboard, but this is the one where I found it at, and this is what I searched in Google. Okay, so that will be it for today.
So the very first book that you have in the syllabus, that one we do have to purchase, correct?
Correct.
Okay.
And I will post information for that book later today, probably, whenever the company gets back to me, because they have to make it for me. But yeah, but for now, if you want, find this discrete math book online and read sections 1.1 and 1.3. Okay. So that will be it for today. If someone can please create a GroupMe account for the class and then share it on Blackboard, and I'll join it. That way, like I said, if there's any type of emergency, if anyone needs to get a hold of me, you can. So yeah. Also, this lecture will be posted to Blackboard. Like I said earlier, all my lectures will be posted in the lecture videos folder on Blackboard. Okay, so y'all stay safe. There's a hurricane coming, so again, stay safe. Don't catch a virus, and be checking Blackboard throughout the rest of the day. Okay, y'all have a good day.
Thank you, Professor.